Hi, hello. Good evening. For today, we will be discussing our last topic for electronics 1, and that is about FET, AC, and DC analysis. So unlike what we did in BJT, we'll just discuss the DC analysis first because some of the parameters that you will be needing in solving for the AC analysis will be taken from the DC analysis. Then right after that, we will already proceed with the AC analysis. So the both DC and AC analysis for FETs are simpler compared with the BJT. Okay, particularly when we are talking about the JFET and the D type, the D MOSFET. Okay, let's begin. For this discussion, we will be talking about the common FET biasing circuits. So what are those? So for JFETs, so we will be discussing three types of biasing circuits for JFET, and that is fixed bias, self-bias, and the voltage divider bias. And then we will be discussing D-type MOSFET. So the biasing circuits that we're going to discuss is the self-bias and the voltage divider bias. So we're going to find out that the analysis, both the analysis for JFET and D-type MOSFET is just the same. So there will just be a little bit of difference when we are trying to draw its transfer curve. But for the load line using the self-bias and the voltage divider bias, we're going to notice later that they are just the same. So when you understand the JFET DC analysis, so there's no problem with the D-type MOSFET DC analysis. So for E-type MOSFET, so as we discussed from our previous video, among these three types of FETs, the different FET that we are talking about is the E-type MOSFET. So because E-type MOSFET doesn't use the shockless equation, unlike your JFET and your D MOSFET. But we're going to see also the similarities between the voltage divider bias in E MOSFET with the voltage divider bias with the JFET and with your D MOSFET. Okay, so before we start, let us have a short review regarding the basic current relationships between our JFETs. So for all the FETs that we are talking about, so what are those? For the JFET, the D MOSFET, and the E MOSFET, we're going to, we say that IG, or the gate current, is always equal to 0. So for JFET, how do we do this? We always see to it that your VGS is always reverse biased so that we can be assured that IG is equal to 0. However, for the D MOSFET and for the E MOSFET, we can apply a positive VGS for an N-channel N-channel D MOSFET and E MOSFET. However, IG will still be equal to 0. Why? Because between the gate and the channel, we place a smaller insulator, the silicon dioxide. So we call that your SiO2. So that will serve as insulator for your gate current, so that it is not permitted to enter your channel. So even though there is all the VGS is all it can be positive for reverse biasing, or sorry, negative for reverse biasing and positive for forward biasing, we are still assured that IG is still equal to 0 because of the insulator placed between the gate and the channel. So that insulator is what we call the silicon dioxide. Okay, so we all know that your ID, or your drain current, is just equal to your source current because your channel is just made up of a same material. Okay, so if it is an N-channel FET, so therefore we have a strip of an N-type material, and if it is a P-channel, so we have an entire strip of a P-type material. Okay, so therefore your ID is just equal to IS. And then what we always use is just the drain current. For JFETs and D-type MOSFET, we make use of your Shockley's formula. So what is your Shockley's formula? Shockley's formula is equivalent to IDSS multiplied by 1 minus VGS all over VP squared. So from the Shockley's formula, we are going to determine the value of ID for a certain value of your VGS. So in that formula, IDSS and your VP are constant. Okay, so this formula is applicable only for JFETs and for D MOSFET. So it is entirely different from a MOSFET. So for a MOSFET, in solving for ID, we're going to we're going to use the formula K, ID is equal to K multiplied by VGS minus VT, or the threshold VGS squared. Okay, so we have your the VGS must be greater than your threshold voltage so that your E-type MOSFET or your E-MOSFET will have to function. Okay, so as we go through with our discussion, we will be using these basic current relationships, and then for FETs, majority of our discussions will be based on graphical solution. So the graphical solution will be based on how we are going to draw your load line and your transfer curve. So the transfer curve was already discussed on the previous video, but we will have a review on how are you going to draw the transfer curve. So it will be very important for you to get a more accurate answer. Okay, so we will be starting with a fixed bias configuration. So this is your JFET. So this is our symbol for an N-channel JFET. So this is we have a source here. So we have a source here, which is your VGG. So take note of your VGG. So since this is an N-channel JFET, that means our gate is P-type. So since your gate is P-type, we have to reverse bias your gate. Therefore, we have to place your VGG here, your negative terminal VGG, to your P-type material for us to make sure that your VGS is reverse biased. Therefore, your IG will be equal to 0. Okay, so this is our complete fixed bias configuration. So just like what we did in BJT, we will be separating your AC analysis from your DC analysis. So what are we going to do? So for DC analysis, all we have to do is to during DC, your two coupling capacitors here, your C1 and C2, will just act as an open circuit. Okay, so if this is an open circuit, that will leave us with this circuit here. Okay, so for fixed bias configuration, since this is a very straightforward configuration wherein we can apply easily your mathematical solution. So what are we going to do? We just have to, so this is now your circuit. So you might be wondering, where does your RG? Okay, so why did your RG disappeared? So this is your complete circuit, and then we have here your DC circuit. So as you can see, the capacitors were removed. Why? Because they act as an open circuit during DC. Okay, so however, where is your RG? So remember, since we said that your IG is equal to 0, so whatever current flowing across your RG, so since IG is equal to 0, therefore, what is the voltage drop across RG? So voltage drop across RG is RG multiplied by IG, but IG is 0, so therefore there is no voltage drop across your RG. It is 0. And what is the effect of a 0 voltage? A 0 voltage means a short circuit. Therefore, your RG here is shorted. So what we have here is just your what we have here is just your VGG and your VGS here, okay? So as you can remember in our BJT discussion, the parameter which is given before was the beta. So for FETs, the parameters that will be given are your IDSS and your VP. Okay, so what we have here, okay, so the formulas that I have shown you earlier, the Shockless formula, the IG is equal to 0, ID is equal to IS, so that pertains to the device only. Okay, so everything changes once we place your device or your transistor into your circuit. So therefore, we need to solve for your ID, okay, at a certain point of your VGS. So what will be your ID if your VGS is of this amount or vice versa? If my VGS is like this, what will be my ID? So we are trying to solve for two values using your single formula, which is your Shockless equation. So we don't have any other formula, just your Shockless equation. Okay, so what are we going to do here is that we're having a KVL here. So I have prepared, okay, so I have prepared your solution here. So I have here the network for your DC analysis. Okay, so this is your VGS, this is your VGG, and this is your VGS. Okay, applying a clockwise rotation or KVL here, I will be having negative VGG minus VGS, wherein I can get, so it is called fixed bias. So it is called fixed bias. Why? Because I have, or I got the amount for VGS right away, and that is equivalent to a negative VGG. So this is only this is correct because we said that your VGS must be reverse bias, and the negative sign here just confirms that your VGS is indeed negatively biased. Okay, so this is likewise very straightforward. So this is the simplest biasing configuration that we can get your answer directly. Okay, so upon getting your VGG, since VGG is a source, so therefore it is a whole number. So that is your supply that pertains to a power supply. So we have here your value, which is VGG. VGS is equal to negative VGG. So upon um, substituting this with our Shockless formula, so ID, we can easily solve for ID. ID is equivalent to IDSS multiplied by 1 minus VGS all over VP squared, wherein your VGS here is now equivalent to your negative VGG. Okay, so this is very straightforward. Upon analyzing the other parameters that we have in our circuit, so going to the output side of your circuit, so we have here your ID. Okay, so you have your negative VDD flowing from negative going to the positive in this direction. So your ID will be entering here. So this is this is your positive point, and then we have minus here, that is your negative point, and then we have here your positive VDS, positive at the drain and negative at the source. Okay, so using KVL again in a clockwise manner, we have here positive VDS plus IDRD minus VDD is equal to 0. So the only thing that is unknown here is your VDS. Why? Because VDD is your source, RD is your resistor in your circuit, so this is usually given. And then we have already solved for ID from our input side. So therefore, we can right away solve for your VDS, which is equivalent to VDD minus IDRD. So what ID are we going to use here? The one which we solved earlier at the input terminal of your circuit. Okay, so since we do not have any resistor placed in your source or at your source terminal, so therefore it is 0 volts. Okay, so it is just shorted, it's just wire. So VDS, like what we have discussed previously in BJT, so that signifies your drain voltage minus your source voltage. But since your source voltage is equal to 0, so therefore we have VD is equal to your VDS. Likewise, VGS means VG minus VS. And since VS is equal to 0, we have your VG, which is equivalent to your VGS. Okay, so actually, the FET analysis is just simple because you have already discussed this in our BJT discussions. So we are just changing the subscripts. Okay, so instead of having emitter, base, and collector, we just have your drain source and then your gate. Actually, your VDS here is just the counterpart of your VCE when we are talking about BJTs. Okay? So this is the mathematical solution, which is very, very simple. It is so straight to the point. Okay? We're in right away we can solve or we can get your answer. However, we have an alternative solution, which is your graphical solution. Although when you have a fixed bias configuration, it is very much advisable to just use the mathematical solution. But if we're going to discuss the graphical solution just for the preparation for our next configurations, so how are we going to apply graphical solution? So the first step is we need to plot your Shockley's equation. So from the previous video, I have already taught you how to plot your Shockley's equation. So the Shockley's equation, so that you can plot your transfer curve, you will be needing different points. Okay, so you will be needing different points in order to plot properly your transfer curve. So usually for the graphical solution, we are using this. If you can still remember, we are using this 4 points. So we usually use this 4 points. So what are those 4 points? When VGS is equal to 0, your ID is equal to your IDSS. So where is that point, class? So that is your Okay, so where is that point, class? So that is this is your first point. Okay, so when your VGS is equal to 0, your ID is equivalent to your IDSS. Our second point is this one. When your VGS is equal to VP, your ID is equal to 0. And then, so that we can approximate your curve further, we can use one or two more points. Okay, so the other points that we have established is that when your VGS, is equal to half, okay, half of your VP or your pinch of voltage, your IDSS is equivalent to, or your ID is equivalent to 1/4 of your IDSS. And then we have another point that we have discussed on the previous video, that when your VGS is equivalent to 0.3 of your VP, your ID is equivalent to half of your IDSS. Although in this example, in this transfer curve, um, we did not place anymore the fourth point, but for more accurate transfer curve, you can make use of these different 4 points. Okay, and then the second step is we're going to find the solution for the fixed bias configuration. So what is our equation for the fixed bias configuration? So our equation for the fixed bias configuration is just your VGS is equal to negative VGG. So since this is a whole number, so this represents an exact location of in your VGS. So this is the graph, shows your characteristic of your device based on your Shockley's equation, and this straight line here represents your network. So your network is represented as VGSQ, which is equal to negative VGG. So the intersection of your curve and your network defines your Q point. So your Q point determines your ID, which is your drain current, functioning at your VGSQ, which is your gate to source voltage. So the intersection of the device and the network specifies the value of your ID and your VGSQ. So your ID here must be equivalent or very, very close to your answer in your mathematical solution that we had earlier. Okay, so the accuracy of your answer when we are using graphical solution will be based on how you are going to draw your on how are you going to plot your Shockley's equation. Okay? Now, for fixed bias configuration, so as I've mentioned before, so these are the different formula, the different sources or voltages that can be asked. Okay, anyway, um, this is very, very simple. Okay, so you just have to remember it. So you may not memorize it because all you have to do is to just derive it from the circuit. Okay, so that is your fixed bias configuration. Now, for the AC analysis for FET is very, what you say, straightforward or very simpler if we're going to compare it with the BJT. So if you're going to remember our BJT discussion, there are four important parameters for your AC analysis. So what are those? You have the input impedance, you have the output impedance, you have the voltage gain, and you have the current gain. Okay? So in AC analysis for fixed configuration, for JFET, what we have here, what important thing that we have here is your transconductance. So your transconductance is the relationship of a change in ID to the corresponding change in your VGS. So your transconductance GM is given by your change in ID with respect to your change in your VGS. Okay? So this is given by the formula 2IDSS. So divide by VP multiplied by 1 minus VGS all over VP. So, as you can see, your IDSS is given, your VP is given in your circuit. The only thing that is not given there is your VGS. However, VGS was already derived in your DC analysis. So therefore, once your VGS is known in your DC analysis, AC analysis is very, very simple. All we need from the DC analysis is your VGS. So if you're going to remember in BJT, we need your IE, emitter current, in your DC analysis so that we can solve for your small RE. So in this case, class, we need your VGS from the DC analysis so that we can solve for your GM or your transconductance. So your transconductance was derived using this. Sorry. Where is that? Excuse me. Sorry. Okay, sorry. Um, the formula for your transconductance was derived using this formula. So it just came from your Shockley's formula. Okay, so this is the mathematical definition of your transconductance. Okay, so this is the change in ID with respect to your change in VGS at a certain Q point. Okay, so what we did in your DC analysis, we get the intersection, and the intersection is your Q point. So that is the change in ID with respect to the change in VGS at a certain Q point. Okay, so your change or your delta there can be defined as the derivative or the DID with respect to dVGS at Q point. Okay, so we have here your D, change in your ID with respect to your change in VGS. But what is our ID? Using the Shockley's equation, so that is equivalent to IDSS multiplied by 1 minus VGS all over VP squared. Okay, so applying your first derivative there, applying your differential calculus. Okay, excuse me. Sorry. So applying your differential calculus. So IDSS being a constant, we can place it here. Okay, so this is an exponent. So you will be placing your 2 here, right? So 2 IDSS and then 1 minus VGS VP. This is raised to 1. Then the derivative of 1 minus VGS all over VP. Okay, so simplifying further, so you already know this from your calculus, okay? So simplifying further, we have here your formula for your transconductance, which is 2 IDSS all over VP multiplied by 1 minus VGS all over VP. So your IDSS is given based on your device, okay? Your VP is given based on your device. So the only thing that we will be needing from your DC analysis is your VGS. Okay, so once you know that, we can easily solve for transconductance. Okay, so if you still remember in your BJT, we have your RE model and we have your hybrid model, wherein your hybrid model was already defined. Okay, so you will not be needing your VGS, your IE anymore. So likewise in FET, we have your GM or your transconductance. So um, in specification sheets, you can also get their values with as your YFS. So in JFET's specification sheets, whenever you see YFS, that corresponds also to your transconductance. Okay, so YFS, YY. So why? Because it is an admittance parameter. So if you can still remember, impedance is denoted by letter Z for impedance, and admittance, which is the reciprocal of your impedance, is denoted by letter Y. Okay, so this is small letter because we are using AC analysis. So F, that means you have a forward parameter, and S because your GM is connected at your source terminal. Okay, so this is an admittance parameter because this is a reciprocal of your resistance. Why? Because this is current over voltage, while resistance is equivalent to voltage divided by the current. That's why it is admittance parameter. So what is the unit for transconductance? The unit for transconductance is Siemens. Okay, so in some older books, admittance parameters are in terms of mho. So mho, that is the reversal of ohm, but in some other books they use already Siemens for transconductance. Okay, so for AC analysis, this is quite simpler compared with the with the BJT. Okay, so input impedance, this is open. So why this is open? Because your gate current is always equal to 0. Ig is equal to 0. And what circuit represents current which is equal to 0? So that is an open circuit. So as you can see, this is an open circuit. And when you have an open circuit, you have an input impedance which is equivalent to infinity. So therefore, all in all, the input impedance for JFET is already equal to infinity. Okay? So the output impedance is equivalent to RD in specification sheets. So RD is represented by YOS. So again, an admittance parameter located at the output, which is also connected to your source. So output admittance is just the reciprocal of a certain YOS. YOS is being written or being specified at the specification sheet of your transistor. Okay? And then we don't have a current gain. So why don't you have a current gain? Because current gain is equivalent to output current with respect to your input current. But what is our input current? Our input current is 0. So automatically, it will become infinite. So therefore, we only have your output impedance, your input impedance, and lastly is the voltage gain. So how are you going to analyze the voltage gain? So this is your complete circuit, and this is your fixed bias configuration. So the blue one represents your transistor or your JFET. So this is open circuit. So this is your transconductance multiplied by your VGS. So GM is in terms of Siemens or 1 over ohms. Okay, this is your VGS. So voltage divided by resistance, it represents a current source. And then if ever there is an RD, so you place your RD there. So we have RG here and you have your RD here. Your RG and your RD they came from your fixed bias configuration. Okay, so all your batteries, your VGG and your VDD was placed by a short circuit, and all of your capacitors, your C1 and C2 was replaced by a short circuit likewise. Okay, so very simple. So your input impedance now is just equivalent to your RG because this is an open circuit. The only thing that we can see at the input is your RG. So you have your answer right away. Your output impedance is the parallel combination of your RD here and your drain resistance here. Okay, in cases that RD is very, very large or it is not given in the circuit, your output impedance is simply equivalent to your drain resistance. For your voltage gain, that is VO all over VI, okay? So your VO is equivalent to your GM, which is your current. So GM, okay, your GM VGS multiplied by your RD parallel RD. So what is your VI? Your VI is equivalent to VGS. So your VGS will just be canceled out, giving us a voltage gain which is equivalent to the parallel combination of your RD and your RD here multiplied by GM. So again, a negative sign there signifies that you have a 180 degrees phase reversal, or simplifying further, you have negative GM multiplied by RD. So we only need 3 parameters for JFET configurations. Okay, so just your ZI, your ZO, and your voltage gain. Okay, so once you know your GM from your DC analysis, your voltage gain is very, very simple. Now, the second type of circuit is your self-bias circuit. Okay, so how does your self-bias circuit looks like? So this is how your self-bias circuit looks like. Okay, so as you can see, we don't have your VGG anymore, but instead we have your RS. So analyzing that further, okay, analyzing your self-bias circuit, okay? So simplifying your self-bias circuit, we have there we have here your KVL. So that will give you minus ID multiplied by RS. Okay, so where does your VGS went? So why didn't we consider the effect of your RG? Because since IG is equal to 0, therefore your RG is equivalent to a short circuit. So all we have there is equivalent to minus IDRS minus VGS is equal to 0, wherein your VGS is equal to negative IDRS. Okay, however, okay, in solving for, so that's your circuit. However, in solving for your VGS, okay, we need your substituting the value for your VGS there. So that will give you VGS is equal to negative ID multiplied by RS, okay, all over VP. We are solving for your ID, but we also have your ID here needed in solving for ID. So therefore, this is no longer straightforward. Okay, so rearranging the formula, we can have uh, we can have this values here because RS is a constant, IDSS is a constant, VP is a constant. So technically speaking, the only unknown here is your ID. However, we have here an ID which is squared, and we have here an ID which is not squared. So we are down to a, what do you call this formula? To a quadratic equation. So this quadratic equation is not very, very difficult to solve because some of your calculators already have your quadratic formula stored in it. So all you have to do is to enter the value of your constants for A, for B, and for C. However, in manipulating this formula so that you can be arriving on a quadratic formula, it may be very tedious task. And what more is that you can have here two values for ID. So when you have a quadratic formula, you have two roots. Okay, so you have two values. So you still have to choose which among those two is the value for your current at a corresponding value for your VGS. So in this format, a very more simpler approach is your graphical solution. So what is your graphical solution here? So the graphical solution, first step, you have to draw, okay? You have to draw your transfer curve from the Shockley's formula. You have to plot your Shockley's formula. And then after that, you will be drawing your load line. Okay, so how are we going to do that? So for the graphical solution, for the graphical solution, again, you have your first point here, you have your second point here, and you have your third point here. If you still need another point, you can use the value which is VGS is equal to 0.3 of your pinch off voltage. That is equivalent to your IDSS divided by 2. Okay, for your fourth point. So upon applying the first step, we will now be drawing your um, your line. So how are you going to draw your line? You are going to make use of this one. So we are going to make use of this formula. Our formula is VGS is equal to negative ID RS. Okay, so in order for us to draw a line, we need to plot 2 points. So what are those 2 points that we need to plot? So first is when we let your VGS is equal to 0, ID is equal to 0. So our first point actually lies at your origin. Okay, so your first point lies at your origin. And then the second is we have to assume. Okay, so we cannot get any more values here because if we let your ID is equal to 0, likewise, that will give us VGS is equal to 0. So what we need to do here is to assume. So for example, what will be my VGS when my IDSS is equal to half? Okay, so that will become my second point. Okay, so after doing that, I now have my 2 points. Okay, so this is my first point, and this is my second point. So this is my VGS when my ID is equivalent to half of my IDSS. So IDSS is given, RS is given, so we can have here an actual value for your VGS. Take note of the negative sign. We are always at the left side of your quadrant because we have an N channel. So for P channel, you are at the right side of your quadrant. Okay, so we draw the straight line. This is your straight line. So since our equation is linear, so therefore your line is linear, is a straight line, and then the intersection of your transfer curve from your straight line is your Q point. Projecting this to your current, that will become your IDQ, and projecting it downward, that is your VGSQ. Okay, so as simple as that. For AC analysis, it's the same. Okay, since we have CS here, so RS will be bypassed. Okay, so your ZI will be equal to RG, your ZO will be equal to RD, parallel your drain resistance, and then for the voltage gain, it will be the same. So it is very, very simple. This is the effect if we remove your CS or your bypass capacitor at your source. So we can see the effect at the voltage gain. So the voltage gain will somewhat be reduced, just like what will be the effect when we have your when you don't have the emitter bypass capacitor in your BJT. Okay. So last is your voltage divider bias, okay? So for the voltage divider bias, excuse me. I'm sorry. Sorry. Okay, so for the voltage divider bias, so I will be showing you the mathematical solution and then later on the graphical solution. Okay, so in here, so we will be placing a value for VG since we said that IG is equal to 0. So therefore, the current which will flow across your R1 is just the same current which will flow across your R2. So we will be calling the voltage across your R2 your VG or your gate voltage. Okay? So your VG is equal to the voltage across your across the divider resistor R2, and VG is equivalent to R2 multiplied by your VDD divided by R1 plus R2. Now, using Kirchhoff's voltage law or KVL at this portion, we have here your VG plus VG minus VGS minus VRS. So VRS is equivalent to IS multiplied by RS, but since IS is equal to ID, then we can have here ID multiplied by RS. Okay, so the Q point is established by plotting a line that intersects the transfer curve. However, okay, so if this is your VGS, we can replace that mathematically using your Shockley's formula. And that is equivalent to IDSS minus, but what is VGS? VGS is equal to VG minus IDRS all over VP. However, VG is already a whole number, so we can solve for that. RS likewise is a whole number. However, so upon simplification or simplifying this formula, you again will end up in a quadratic equation. Okay, so just like what we have in a self-bias configuration. However, we can simplify this further by just using your graphical solution. So what is your graphical solution? Again, your first step is we're going to plot the line by plotting 2 points. Okay, so what are your 2 points? So we will be using this equation in plotting your 2 points. So we will not be using the origin. Okay, so we use the first point at the origin using the self-bias configuration. So for voltage divider, we do not use the So for voltage divider, we do not use the origin, okay? But we can establish 2 points here. So how are you going to establish those 2 points? So first, we're going to set your VGS be equal to 0, and we're going to solve for your ID. Your ID is equivalent to VG divided by RS. So we have already solved for your VG. VG is equivalent to what? VG is your VDD multiplied by your R2 all over R1 plus your R2. Okay? So, when your ID is equal to 0, VGS is equal to your VG. Okay? So, step number 2, you have to plot the transfer curve by plotting IDSS, VP, and calculated values of your ID. So, step number three, um, the Q point is located where the line intersects the curve. Okay? So, we have here the formulas for voltage divider bias, okay? For AC analysis, it is just the same. The difference is for ZI, R1 is parallel with R2, okay? But as you can see, for the output impedance and the voltage gain, it will just be the same. So I have here your sit work number 1. Okay, so for your sit work number 1, I will be assigning or I will be placing a drop box wherein you can submit your circuit number 1. Okay, so I want you to use the graphical solution for this sit work. Okay, so because it is said there that you have to draw the transfer curve. Anyways, that is for JFET. Now, for D-type MOSFET circuit bias, it is just the same. Okay? So it is just the same with the uh, JFET. So it is just the same with the JFET. The only difference is that the depletion type MOSFET can operate with positive values of VGS with ID values that can exceed your IDSS. So for JFET, your ID are always lesser than your IDSS, whereas for the MOSFET, a possible drain current which is greater than your IDSS. Okay? So we'll go right away with the example. So this is a what type of configuration is this? This is a voltage divider, okay, configuration, but this time we are going to make use of your um, um, DMOSFET. Okay, so look at the symbol. So we are asked to define your IDQ, your VGSQ, and your VDS. Okay, so what's your first step? Hey Google, turn on dining room. Hey Google, turn on dining. Okay, so the only difference for a D-type MOSFET is that we need a point that is located at the at a certain positive values for VGS. Okay, but the rest, it will just be the same. Okay, so for first step, what are you going to do? We need to sketch the transfer curve. So our given IDSS is 6 milliamperes and our given VP is negative 3 volts. So as you can see from our table here, when your VGS is equal to 0, your ID is equal to your IDSS, which is 6 milliamps, okay? When your VGS is equal to your VP, which is negative 3, your ID is equal to 0. When your VGS is half of your VP, so in this case, it is 1.5 volts, that is equivalent to 1/4 of your IDSS, so that is 1.5 milliamperes. And then, when your VGS is equal to 0.3, of your VP, which is 0.9, that your ID is half of your IDSS, which is in this case is 3 milliamperes. So for JFET, you stop here. Okay, so for JFET, this is already enough in solving for the transfer curve. So what differs your DMOSFET from your JFET is that we need an additional point. Okay, so we need an additional point which represents a positive VGS. Okay, so let us assume I have a positive VGS which is equivalent to positive 1 volt. So upon solving using the Shockley's formula, I can have an ID which is equal to 10.67 milliamperes. Excuse me. Okay, so I have here 4 points plus a point with a positive VGS. Then I can draw the transfer curve. Okay, for the voltage divider configuration, I can solve for I can use this formula. VGS is equal to VG minus ID multiplied by RS. Okay? So when your VGS is equal to 0, my ID is equivalent to VG all over RS. So solving for VG, this is my formula for VG. VDD multiplied by R2 divided by R1 plus R2. So I can have here 1.5. I have here 1.5 volts. Okay? So that will give me ID which is equal to 2 milliamperes. When my ID is equal to 0, VGS is equal to VG, which is equivalent to 1.5 volts. Okay? So this is my straight line and this is my transfer curve. Okay? So what I do now is you have to plot. So you need to plot this properly so that you can have an accurate, okay? So you can have an accurate answer. So these are the steps, okay? So just like what we do, so these are the steps, and then this is your answer. Okay, so from look at the 4 points, these 3 points and this 1 point here, that represents your blue curve, and then the straight line is represented by these 2 points, the 2 milliampere point and the 1.5 volts. Okay, so the intersection, so what is the intersection? IDQ, that will give you 3.1 milliamps, and your VGSQ is your negative 0.8 volts. Okay? Ma'am, what if my answer is 0.85 or 0.9 or 0.75 or 3.2 or 3 milliamperes? So I think we can have a tolerance there. We can have a specific tolerance as long as you can show your solution very properly. Okay, because if your answer doesn't show your solution, or it is very far from the graph that you have provided, then we cannot consider your answer. So really, it's on the graph. Okay, so this is the AC equivalent model, just the same. So the AC equivalent model for JFET and D-type MOSFET are just the same because technically they make use of the same formula. Okay? So for a self-bias D MOSFET, it's the same. Okay? So we have here, first step, you draw the curve. So you have to draw the curve from your IDSS, which is 8 milliamperes, and your VP, which is equal to negative 8 volts, okay? And then you have an additional points when your VP is half, which is negative 4, your ID is 1/4 of your IDSS, which is 2 milliamperes. When your VGS is 0.3 of your VP, which is 2.4 volts, your ID is 1/2 of your IDSS, which is 4 milliamps. So the difference of a D MOSFET and a JFET is the additional point. So for example, we have here, we placed a positive values of your VGS, which is equivalent to 2, positive 2. So that will give you an ID which is equivalent to 2.5 milliamperes. Okay? So for a self-bias, what is your formula for self-bias? So your formula for your line is VGS is equal to negative ID multiplied by your RS. Just like the self-bias in your um, uh, JFET, okay? So the first point is at the origin. Again, when your VGS is equal to 0, your ID is equal to 0. The second point you have to assume, okay? So the second point you have to assume, so let us say VGS. What if my VGS is equal to negative 6? So ID is equal to 2.5 milliamperes. So this is the curve. These are the points for your curve, and points for your these are the points for your straight line. Okay, so let us see your solution. So these are your solution. So the blue curve is based on your checklist plot, and then the straight line is based on your network. So in the intersection, which is IDQ, which is 1.7 milliamps, and your VGC-SQ is equal to negative 4.3. So in solving for your VDS or your VD or your VS, so you will just be using your value of ID in solving for the other unknowns. Okay, so that is your self-bias D-type MOSFET. So really, your answer will be dependent on how you are going to plot your curve properly. Okay, now for E-type MOSFET, this is somewhat different, okay, because E-type or enhancement type MOSFET doesn't make use anymore of your shock list formula. So the transfer characteristic for E-type MOSFET is very different from the JFET and the D-type MOSFET. So this is how we are going to draw the transfer characteristic. For E-MOSFET, the graph is at the right side. Why? Because we will be needing a positive VGS. So it is said to be enhancement type, enhancement only. So depletion or reverse biasing your VGS won't let your E-type MOSFET function. So for your E-type MOSFET to function properly, so it should be in the enhancement or the forward bias mode. Okay? So what is given? So what is given in your eMOSFET is that all circuits or all voltages, as long as it is below VGSTH, you don't have any current. So for your current to conduct, it should exceed your threshold voltage. Okay? So we have here a definition usually given in the parameter ID on with its corresponding VGS on. So what is your voltage so that your current is like this, of this value? Okay? This is the first type, the E-type MOSFET feedback circuit, wherein when IG is equal to 0, so therefore it will look like this. Okay, it is shorted. So the drain is directly connected to the gate. So the drain to source and the gate to source is just the same. So therefore, your VDS is just equal to your VGS. So our working formula here, class, is your VGS is equal to VDD minus IDRD. Okay, so VGS is just equal to your VDS. So how does it functions? So step 1, we are going to plot your line using this formula. Okay? We're going to plot your line using this formula. So VGS, VDD minus IDRD. So when ID is equal to 0, your VGS is equivalent to VDD. And then when your VGS is equal to 0, your ID is equivalent to VDD all over RD. Second point is you have to draw the transfer curve, okay? And then we get the Q point, okay? So using the value of Q point, you can solve for the other parameters. Okay, so let's have an example. Let us determine the value of your IDQ and VGSQ. Okay, so in this case, class, we are given ID on 6 milliamperes. We are given VGS on 8 volts and VGS TH equal to 3 volts. Okay, so we have to establish points first. So before we can get the point, we all know that below 3 volts, all of your current is equal to 0. Okay, so above 3 volts, your current starts to increase. Okay, so we need to establish first the value of K. So we can solve for the value of K because usually K is not given in the specifications, but a certain or a pair of ID and VGS is given. So that is what we call your ID on and your VGS on. So using that value here, we can solve for your K, that is 6 milliamperes. So that is 6 milliamperes divided by 8. So this is your VGS on minus 3 squared. So that will give you 0.24 milli. So what is the unit? Ampere per voltage squared because this is V squared. Okay? So your VGS, so this is your, the first point is 0. The second point is your ID on and VGS on. Then we can supply other points. So for other points, we can say that what if your VGS is equal to 6? So when your VGS is equal to 6, we can use the value of your K here multiplied by 6 minus 3, okay, squared. So that will give you a current which is equivalent to 2.16 milliamperes. So if you needed one more line or one more point, that will give you VGS is equal to 10. That will give you an ID which is equivalent to 11.76. Okay, so you have 4 points already. Then you can plot the transfer curve. Okay, how about the line? So the line is given by this one. So you have your VDD and you have your VDD which is 12 volts and your VGS which is equivalent to 6 milliamperes. So this will provide your, these points here will provide your straight line. Okay, so when you graph, okay, how does the graph looks like? So this is your graph. Okay, so where are your points? So your all points below 3, so that is 0. So upon entering 3, so you have your ID on and your VGS on, and then you have your 6, and then you have your 10. Okay, so this is your transfer curve, followed by your straight line. This is your straight line, your 6 milliamperes, and your 12 volts. Okay, now the intersection of your curve and your straight line, which is around 2.75 milliamperes and 6.4 volts, will be your answer. Okay, ma'am, what if it is 6.5 or 6.3, or what if it is 2.8 or 2.7? Okay, so that will be acceptable as long as your graph will show it. Okay, so that will be your answer to that. Okay, so next is the voltage divider biasing. So for the voltage divider biasing, it is just the same with the voltage divider for JFET and for the MOSFET. So the only difference is the transfer curve, but the line, it is the same. Okay, so the straight line will be the same for JFET and the MOSFET because they are the same voltage divider. The only difference will be the curve, okay, on how you are going to draw the curve. So these are the steps, okay? So we will be plotting the line, we're going to plot the transfer curve, and then we will be getting the intersection of your Q point, and then using the value of ID and your VGSQ, you will solve for the other circuit values, okay? So for this example, okay, so for this example, how do you draw the curve? Okay, from the given value, we solve for K. We solve for K using your ID on, which is 3 milliamperes given, and 10 volts, which is your VGSTH on. So that will give you 0.12, okay? So all voltages lesser than 5 volts, you have zero current, okay? So current will start to increase upon reaching 5 volts. So we can have an additional voltages. So let us say, what if our VGS is 15? So using the value for K here, that will give us 12 milliamperes. And then when your VGS is equal to 20, that will give you 27 milliamperes. So this will be representing your curve. Okay? So for the line, you need to solve for VG using voltage divider formula. So that will give you 18 volts. And then you're going to assume that VGS is equal to 0. That will give you an ID value. And when your ID is equal to 0, that will give you a VG value. Okay? Then what you have to do, you can draw the straight line. You can draw the curve, and then you get the intersection. So the intersecting point will define your Q point. And this is your answer. Okay? So you can compare the points. You can compare the 4 points from this and the straight line from this. So your answer will be based on how accurate is your graph. Okay? So the voltage divider are the same. So the only difference is the blue curve. Okay? Because of the formula that we have used in establishing that curve. For E-type MOSFET AC equivalent, again, GM and RD can be found in specification sheets. Okay, for mathematical purposes, coming from the formula, your GM is equivalent to 2K. So K is given, you can solve for your K, VGSQ minus VGSTH. So the thing that you will be needing in the DC analysis is your VGSQ. Okay, so your GM and RD can be found in specification sheets. So your GM is in the form of your YFS, and your RD is in the form of your YOS. Okay? So these are your input impedance, your output impedance for, and your voltage gain for feedback bias, and these are your input impedance for your voltage divider bias. Okay, so all of them, they are in a form of a common source, just like common emitter for BJT. Therefore, almost all of them have a voltage gain which is negative, or the output voltage is out of phase with the input voltage. Okay, so that's it. There's another set work. So I will be placing a uh, I will be placing a drop box for this set work. Okay, so it will be due about next week. Okay, and I will be placing some announcements since it is, I think, impossible for us to have a face-to-face exam due to the extended quarantine, especially for students. So I will be placing some important announcements. So please keep posted. Okay, so if I will be giving an assessment, an exam, I will not accept late assessment exam, because I will be basing mostly of your grades from there. So please keep posted on when will I be giving that assessment. Okay? So this will be our last topic for electronics 1. So you have to understand these topics very carefully, because we will use this in our electronics 2 discussion. Okay? So where we are going to end this electronics 1, that is when we're going to start with your electronics 2. Okay? So FETs, if you will be visiting semiconductors industries, we're going to find out that in IC technology, FETs are most widely used compared with the BJT. Okay, why? Because of its construction, it is very, very simple, right? So you only have one P-type and you have only one N-type channel. Likewise, you can interchange your drain and your source. So it is very, very flexible once you place your FETs or your MOSFETs in your integrated circuit. So in the industry, in the semiconductor industry, FETs are really more used compared with the BJT. Although if you will be computing for the gain, FETs have a way smaller gain compared with the BJT. But in electronics too, we will be discussing cascading. So inside your IC, we usually cascade several transistors. So the smaller gain, we can make that a little bit higher. Okay, but in the industry, really, FETs are more widely used compared with the BJT. Okay, so that's the difference between the two. So we will be still continuing those discussions when we go to electronics. So you have to understand it very, very well. Okay, so try to answer yours, it works. Okay, so um, just stay at home and be safe. Okay, so watch the video, study the video, read your textbooks, try answering your problems there, and then you have to review because I will be announcing when will be your assessment. Okay, so thank you for listening and have a nice day. Bye.